Thank you, Mr. Chairman, Professor Zhang, and ladies and gentlemen. Thank you for staying late here now. Okay, I'm introducing a bit of the Taiwan geology, especially on CO2 geospatiations, and also on the monitoring techniques. And indeed, this is a coordinated effort. For example, many of my slides are provided by my co-workers, like in the Taiwan CPC Petroleum Company, and the Sinotech, and the E3. Okay, so, and this project has been funded by, firstly from 2007 to 2009 from E3, and funded by Bureau of Energy. And also from 2010 until now, it has been funded by Ministry of Technology. So this work has been ongoing for quite a few years. This is my outline. Firstly, I would like to give a brief introduction about how CO2 is sequestered in the surface, then on Taiwan geology, and then for a little bit of simulations. And because Taiwan, we have a pilot test site, but so we carry out many simulations, and we hope that we have surveyed a lot of baseline monitoring techniques like seismic and electrical survey. So we applied many monitoring techniques as a baseline survey. So I will also introduce some in the future that we'd like to carry out what kind of monitoring techniques in the geological sequestration of CO2. And then finally, with the final risk assessment using HSE for the geological storage, and then a brief conclusion. So this diagram shows the general scenario for Taiwan, how we like to store the CO2 in the subsurface. I think we have two options. Firstly, maybe in the onshore, and then or in the offshore. So in the onshore, we know we have for example, in the northern Taiwan, we have a few gas fields, like Diezhanshan, this gas field. This gas field is the largest one in Taiwan. That has 1 trillion cubic feet resources. Then this, for example, this is the gas field. So if we store CO2 in the depleted gas fields, and this is one option. And the other one is that the site may lie just neighboring the power plants. Because beneath the power plant we have very thick sedimentary rocks, but the rock, the strata, it is not flat. It is gently dipping toward the east. For example, the diagram shows this. The strata dipping toward the east because of the weight of the Taiwan mountain. And the degree says around 1 to 5 degrees. So it's sloping to the east. And so in this case, if we injected CO2 in the subsurface, in the reservoir, and kept by very thick steel rock, then the CO2 would migrate toward west beneath Taiwan Strait. Then our offshore options, of course, we have two scenarios. One is structural traps. The other one is the deep saline formations. And this diagram also shows that actually those CO2 will be stored beneath the surface, say beneath greater than the depth of 800 meters. So more, perhaps in the 1 kilometer or 2 kilometer or 3 kilometer in depth. So in this case, it is separated from in the near subsurface. For example, we use a lot of groundwater. And the groundwater usually comes from a few tens of meters or a few hundreds of meters. So actually, it is a separated system. The CO2 is in the deeper part, and the groundwater is in the shallow part. And in between, there's an impermeable layer that separates these two systems. And in Taiwan, we have very good arrangement for this kind of system. Say this is reservoir, denoted by the brown color, and the blue one is the steel rock. So we have 3 pairs, similar situation like this one. So a brief introduction on CO2 geospatiations. For example, this diagram shows the porosity, the rock porosity, with increasing depth. For example, from 1 kilometer to 5 kilometers. And the horizontal axis is the porosity. For example, here is the 70% and this is 0%. So this indicates that in the near surface we have a high porosity, the pore space in the rock. But in the deeper part we have a low porosity. But this diagram shows that lying in between about 0.8 kilometer to 3 kilometers, we have a porosity ranging from 30 to 15%. Okay, so it's the pore space looks good. And for this one shows the CO2 density. When the depth increases, the CO2 density increases with different scenario. But the blue one shows the typical one. So you see that below about 0.8 kilometers, the CO2 increase more, the density increase more. So so that's why the geologist tends to store CO2 beneath 0.8 kilometers in this depth. So in this corner it shows that the microscope view of the sandstone. So we see some pore spaces like the blue one, and we have some minerals here. So in between the minerals, it is pore spaces. So when the CO2 injected into the sandstone, actually it occupied in the pore spaces around maybe 50% of the, or up to 60% of pore spaces can be occupied by CO2 and the flowing water. Okay, so essentially there are a few trapping mechanisms for CO2. For example, this is structural traps. So CO2 can be trapped in the anticline, like this one, or the fault traps. Okay. I think in Taiwan, everybody, if we hear about fault, okay, you think maybe it's a leakage. But actually in Taiwan, we have many gas fields. And those gas fields, the trapping mechanism, mostly by fault. So this can also apply in other hydrocarbon fields in the world. That the fault usually act as a barrier for hydrocarbon migration that can trap good oil and gas. In a similar case, that it can also trap CO2 in the subsurface. Also the well traps, or in this one, there's no traps. But if you put CO2 in the subsurface with the reservoir, and on top of the reservoir there's a CO rock. So because there's no trap, and the CO2 is less dense than the brine water. So in this case, the CO2 will migrate upward. So in this case, it will migrate toward these directions. So through the migration, that the CO2 will fill in the spaces in between. So on the path of the CO2 migration pathway. So in this case, we should find the reservoir which is very continuous, not isolated. So study of the reservoir is very important. So we have to make sure that this reservoir extends, say, a few or tens of kilometers. Then we can have a good coverage then to the migration path. Then during the migration, then the CO2 will dissolve. When the CO2 put in the surface, then the CO2 will easily dissolve in the water. It's like this one. So it is like the water that we will drink, the sparkling water. Sparkling water, there's a lot of CO2, right? So it's like this one. The CO2 will dissolve into the water, and the brine water without CO2, it is less dense than the water with CO2. So that once the water is with dissolved CO2, it is denser. So in this case, the dense proof will actually sink in the subsurface. So they never come out to the surface. So that's also very good mechanism. But through numerical simulations, they found that this dissolution solubility trappings made the total amount of injected CO2 made totally dissolve in the formation water maybe during 10,000s of years, so it's quite quickly. So this is also a very good trapping mechanism. And there's another one. This one shows that the blow-up for very micro scale of the reservoir. The CO2 would migrate over this direction, okay? Then some of the CO2 will be trapped by the capillary pressure. So capillary forces, then with the residue left behind along the path. So in this case, it's called the residual trappings. And finally, because the CO2 is quite pure, mostly of the CO2 they will form, sometimes will form minerals, like calcite. So in this case, we will have a mineralization checkings. And sorry, this figure is from CO2 CRC. We have many of our friends here. Very good pictures. Then so I said, let's skip this one. Then for Taiwan, this figure shows that the seismicity, many people are concerned about this. We have a lot of earthquake. So for example, the red one shows the earthquake. Then the earthquake with the depth, okay, and the magnitude. So actually we have a lot of earthquake in Taiwan. According to Professor Wu's study, he's an expert in earthquake study. Then he just mentioned with the publication saying that in Taiwan, for each day, we will have 2 magnitude 3 earthquake. And for 2 days, we will have magnitude 3.5 earthquake. So that means we have a lot of earthquake. But for magnitude 3, it is too small to be felt by most of people. So we have a lot of earthquake. So this one shows earthquake mostly occurs in the mountains. Here, this thick black line shows the deformation front. So it is a mountain front. So to the east, it is high mountains. This is the Central Range, and this is the Western foothills. And to the west, it's the coastal plain and the Taiwan Strait. So you can see that mostly the seismicity or earthquake that occur in the mountain, except one area here. In the southwestern coastal plain, we have some earthquake. And this figure also shows that there are some red circles here. The red circles show the gas fields that have been discovered and developed by Chinese petroleum corporations, especially in the northern Taiwan. Okay, and to the west of this one, the color shows the sediment thickness. The sediment means that it is mostly consists of conglomerate, sandstone, and the shale. And for example, we have 2 major basins, Tai Si Basin here, and the Tainan basins. And in between, we have a Beigang Hai. Beigang Hai means that we have thinner sediments, and the basin means that we have thicker sediments. So for the sediments, it is up to, for example, this contour line shows the 8 kilometer thick of sediments. So we have enough thick, the sediment thickness is enough for CO2 geospatial. And this one also shows some active faults. This black line shows the active faults. You can see the active fault mostly distributed in the western foothills. So in this case, we have a lot of thick sedimentary rocks, and especially in this case, that in the Taiwan Strait, deep saline formation is a good option for CO2 geospatial, and also for the western coastal plain. And in the western foothills, because there are many structural traps or depleted gas fields, so we suggest that in the western foothills, that depleted gas field is very good options for CO2 geospatial. And this figure shows the geology, and the red one shows the active fault, and also the major stationary source of CO2, the major emitter in Taiwan. The number 1 is the Taichung power plant here. And the number 2 is the Mailiao for Formosa plastics. And for the Taichung power plant, it was ranked first number one. That emit CO2 annually for around 40 megatons. Then the third one is in southern Taiwan, and the fourth one is in northern Taiwan. But most of the CO2 major stationary sources actually located along the western coastline. So that means if we can find good sites to CO2 geospatial, especially along the coastline, that would be a good option. And the white circle shows the gas fields, as I mentioned before. So I have to emphasize that those gas fields has been there for a few millions of years. And they still hosted gas in place. And then we can discover and then produce those gases. That means those gas, they remain intact and then experience thousands or tens of thousands times of earthquake. Because we have Taiwan, and the Taiwan is because of earthquake. Then thrusting and uplifting, then that create Taiwan. So that means if we, similarly, those structures that can endure the earthquake shaking without leakage of the gas. So in a similar situation, if we put our CO2 in the subsurface with good size selections, then it is very highly likely the CO2 can be stored in place in the subsurface and endure many times of earthquake shakings without leakages. So this is a stratigraphy that shows the pairs of the seal and the reservoir rocks. For example, from the top to the bottom, actually the vertical axis shows the geological time. So for example, this is Oligocene. Oligocene is around maybe 30 million years ago. And the top is the present day. So from the base to the top, we have many different formations. They are all silicic rocks. So for example, but we divide it into three pairs, three systems of CO2 geospatiations. The shallowest part is here, Jinshui Shale. Jinshui Shale is around 100 to 300 meters thick shale. Shale means that it is very fine grained and the permeability and the porosity is very low. So that it is impermeable. So that is a good caprock that would seal the CO2 in the subsurface. But in the more deeper part, we have a Dalu shale. And also beneath that we have a sandstone, Beryl sandstone. And the yellow one shows that it is a sandstone. In the deeper one, we have a Beeling shale and even sandstone packages. So indeed, in Taiwan, we have three systems, three geological sequestration systems here. Yeah, I forgot to show that. Here shows that we have many gas fields in Taiwan, and this shows the different gas fields. And those gas fields, the reservoir rocks. So the reservoir, you can see that mostly situated beneath the Jinshui Shale. So beneath Jinshui Shale, we have multiple zones of reservoir rocks here. So that indicates that this has been existed and has been trapping a good amount of hydrocarbons for millions of years. So similarly, we can put CO2 in the similar systems, either in the deep gas field or in the saline formation in the western coastal plain or in the Taiwan Strait. Okay, so some of the rocks, they are too shallow or some of they are too deep. So this map is provided by Sinotech. So they map out the different types of spatial distributions of these three systems. For example, like this one and here, this one, why we choose this one? Because first, for example, in the Taoyuan Tableland and the offshore area, there's a very less seismicity, almost no earthquake there. And also in in the Changhua coastal plain and the Yunlin area in the east offshore area, there's very few earthquakes. So they are all very ideal sites for CO2 geospatiation. And also for onshore structures, there are many structural traps and also depleted gas field, especially in the onshore. But in the southern Taiwan, there's still some options for CO2 geospatiation. So let me show you one example. This example is from central Taiwan. So Zhuoshui Sea is here, around here. And this is Taichung City. Okay, and this is the deformation front, and this is coastal plain. We carry out many seismic survey, and let me show you one seismic section from northwest to the southeast. So this seismic section shows that the left one is the offshore seismic section, and the right one is onshore. So you can see there's almost no fault here, like corresponding very few or no earthquake in these regions. But it's a pity there's a gap here. Why? Because it's too shallow. It is too shallow to conduct seismic survey. So we like the Japanese example, how they can conduct 3D seismic survey and 2D seismic survey in the shallow water, especially very close to the coastline. So you see the ideal reservoir rock is around here in these regions, and the Jinshui shale is in this part. So if the site is located somewhere here, then we inject the CO2 with a deviated well. For example, the injection point will be beneath the Taiwan Strait and a few kilometers up the coastal line. Similar the case like the Japanese Tomakana case. So, and because it's dipping toward the east, the CO2 flow will migrate toward the west. And this example is in the Taoyuan Tableland. We are now somewhere here. Here is Taipei City. And Taoyuan is to the south of the Taipei here. And this is the uplifted tableland. So there are some major CO2 emitters, like marked in stars, like this one. So I will show you one seismic section and two seismic sections in the onshore and the offshore. So this one shows that actually here there are very few faults, but there are some in the offshore, but they are not active faults because they have been buried by Pleistocene sediments, so it is inactive. But the geological structure seems good. So we summarize the reservoir rocks. So doing a first order screening for calculating the capacity in Taiwan. So we use many wells provided by CPC, and to choose the reservoir rocks, the sandstone, lying in between 800 to 3,000 meters intervals in depth. So in this case, we selected for sediment the sandstone thickness thicker than 5 meters. So we add up the total thickness of those sandstone, then come up with this isopac maps. So this one shows that, especially in this area, we have the thickest reservoir rocks, but here we have a thinner one. So we divided the ridges into different sectors from north to south, and divided into like a coastal plain, or from the coastline and up coastline to 25 kilometers of the coastline, or 25 to 50 kilometers. Okay, so we divided into different sectors. Then using the volumetric methods, the same with DOE in the US, using this formula, the volumetric method to calculate the capacity for all these regions. So the final number is here. So the number is 55.9 billion tons in all the area. But please remember that this is the first order approximate for the basic capacity for Taiwan. If we are going to investigate or to select sites, we have to do more seismic survey or even drilling to ground truth the thickness of the reservoir or even the capital rock to better characterize the geological condition for each site. So this figure shows that it's quite promising for Taiwan. We can have a lot of pore space to store CO2. So this is the saline formations. And for CPC, they already also carry out computation on the capacity for the onshore structures. Sorry for our foreign guests, this is in Chinese. So, but these are many different types of structures. And also their area, there are different parameters. But the total sum for the onshore structural traps is around 2.8 billion pounds. So it's still a large amount of capacity. So in the future, once we are going to select the geological sites, we will follow strictly the international standards. For example, should we point out if we have a good positive indicators for the reservoir or the capital. Okay, so we will follow strictly for the international standards. Then we also carry out each week. For each colleagues in each week, they also carry out some simulations. I will take in just one example because my colleagues, they have already carried out many scenario and simulation in different areas. I would like just to point out using one example. And this example is from Taoyuan Tableland, that is offshore area. So for example, in this area, and this is the 3D geological model, And this shows the stratigraphy, the rocks. So here, this is the Jinshui Shale. This one is the cap rock. It is around 100 meters thick. Then beneath that, we have a Guizhulin KC and the Nanzhuang Formation. From around 1,000 meters to around 1,700 meters. That means in between this, there are multiple reservoir zones for the reservoir rocks. So in this case, the scenario is that we have 2 injection wells in this area. They are double injection wells. And there's a fault. Fault is more offshore in this area. And the result shows that for Guizhulin and the Nanzhuang Formation, for Guizhulin they can store annually about 5 megaton by 50 years. And so in total, if the injection period is 50 years, and in this side for the Guizhulin and the Nanzhuang Formation, that can host around 250 megatons. So this is also a good amount of CO2 capacity. And the simulation also shows that once it is injected, and the CO2, the plume, will migrate westward beneath the Taiwan Strait, so far away from our onshore area, that would mitigate the risk. So somebody may think that is that CO2 sequestration is safe or not, but actually from my CPC colleagues, they pointed out that actually since 1990s, that CPC already injected the gas, natural gas, in the underground. So it is carried out since 1990s, and it is injected in the depleted gas reservoirs in the depth around 2.6 kilometers. So that will supply the gas fired power stations, and there are 9 injection wells. So the injection technology already existed in terms of the gas injections. So injection production also mature technology. They also can monitor the pressure, temperature, and the inventory monitoring, and the modeling simulations. So they are over 20 years operational experience that our CPC colleagues they already have. So actually, this is not the only case in the world. In the world, there are a lot of this kind of natural gas underground storages. So around 600 projects. So it's been carried out for a long time. So actually, for the injection, the gas injection and production, actually is a quite safe and proven technology in terms of gas injection and production. So this is a diagram showing the scenario like injection into gas storages. Then there are some way of that monitoring the pressures and monitoring where the gas will go. So let's compare to our CO2 sequestration and CO2 study. In Taiwan, though we have studied a few years, but we are now in the initial phase of CO2 project development. So sometimes we are in here. We are spraying site and identify a good size for pilot test. But our, as mentioned by Dr. Hu, that the Thai Power Company and also CPC, they already selected specific sites to carry out pilot tests. So according to IPCC, there are monitoring programs to carry out in order to prevent or to monitor some leakages or to prove the safety contaminants of the CO2. So there are multiple scenarios that already stated by previous speakers, so I will skip this slide. So in this case, we have, of course, there are many different monitoring techniques, both in the onshore and also in the offshore. So the monitoring techniques can be broadly classified as operational, verification, and assurances. So I will probably speak about separate into from like in the area in the atmospheric monitoring techniques. I'd like to emphasize again, because Taiwan, we have carried out a CO2 study for a few years, and mostly we haven't at the pilot test site. So, but we have carried out many baseline survey. So, for example, the atmospheric monitoring techniques has been carried out by many researchers. So it is also existing technology in Taiwan. And for a near surface, like we have to make sure the groundwater is not contaminated by CO2, or if the CO2 has been leaked to the near surface. So there are many different types, like geochemical monitoring in the soil or weather zone, or geomechanical monitoring of shallow groundwater, or using the high resistivity to detect if there is any CO2 leakages. And also in Taiwan, if CO2 injected into the subsurface, sometimes we have a ground displacement. And the displacement, like in North America and North Africa, is the Insala gas fields. The displacement is around 1 centimeter. It's quite small, but we can use the INSAR technique to detect the ground deformations. So all these techniques, most of them are existed in Taiwan research community. For example, like Professor Yang in NTU, they can study the soil here, the gas composition and other composition of the soil to detect if there's any CO2 leakages. And this is subsurface monitoring. And the subsurface monitoring, there are different kinds. I will not read one by one, it's too long. So I summarize maybe just there are two important methods. One is seismic methods, the other one electrical techniques. So, for example, we use this as an example from Nagaoka, from Japan. From their survey, they found that this is the velocity of the formation, and this is the resistivity of the formations. And this one shows that there is no CO2 in the pore spaces. But if the CO2 occupy the spaces, say 20%, 40, or 60%, so the resistivity and the velocity will changes. So that means we can use this joint parameters that we can detect the CO2, the plume, the migrations. So for VP, we use seismic methods to detect the CO2 plume where it migrate or the distribution of CO2. But the limitation of VP is that it is useful for low concentration, say less than 20%. But if the concentration is between 20 to 60%, the change is very small, so no use for VP. But for resistivity, it is less sensitive for low concentration of CO2, but very sensitive to high concentration of CO2. So if we can perform the joint inversions of the seismic velocity and also the resistivity, that we can ideally to quantify the amount of CO2 being injected or the spatial distribution of CO2. So in this case, seismic is quite important, and also electrical techniques. So for example, this has been carried out by my colleague, Professor Wang. They can conduct a 3D seismic survey. For industrial commercial 3D, it's very expensive. But for our poor man's 3D, it's very cheap because we are poor. So Professor Wang, he can conduct 3D seismic by using his vibro size, this one. And there's a vibrators in the vibrate on the ground and send somewhere to the surfaces. So like an image the surface. For example, this example is from here, and this one is in the Taoyuan tableland near the Datan gas-fired power plant. So in this case, they can show the 3D structures, the 3D seismic in this area. And then it shows that there's no fault here, and the geological condition is quite good for geological explorations. And this one is from Nagaoka, it's a Japanese example. They shows the time-lapse the different velocity survey. So the difference between this one looks very similar, but the difference between these two surveys that gives the CO2 plume and even the concentrations. So this is a velocity study, and also this one is from Cranfield, from Mississippi, a U.S. example, showing that there are two wells. the monitoring and the injection wells. So in between, they measure the resistivity. So that before and after, they show the resistivity changes and they can detect the proof where CO2 been ejected. And again, CO2 in the subsurface, then we should say take some sample from the pore spaces to study the CO2 composition. Okay, for example, like this one, this is in the Australia outward example, from CO2 CRC. This one is injection well, and this is a monitoring well. And the CO2 migrate here, then been tracked by this boat. So this boat, again, is a barrier for CO2. And this similar technology has been developed by my colleague, the E3 colleagues. They call it ChemWish. The previous slide is the YouTube, and this one is ChemWish developed by E3. They can sample the subsurface fluids in deep subsurface. Okay, because maybe I go to the conclusions because I'm running out of time. Okay, so the conclusion is that Taiwan has an excellent geological condition for CO2 geospatiations and a huge capacity for CO2 storage, around 48.7 billion tons. Then we suggest that the pilot test site for deep storage scenario, especially for deep gas field and the deep saline formation, need to be implemented as soon as possible. Then various monitoring techniques that are tailored to Taiwan's geological condition should be developed quite soon. Okay, thank you for your attention.